Hi everyone. Next we're going to learn about cell potential, or in other words, cell voltage. And we have some kind of definitions to go through in order to be able to talk about this properly. A galvanic cell has the ability, we said, to push electrons through that external circuit. And the magnitude of the ability is expressed as a potential. So a potential is the magnitude of the force that pushes the electrons through the external circuit. And how we measure that potential is expressed as a unit called the volt. So the volt is listed as a capital V to signify that unit. So it's the SI unit of electrical potential. So it measures the amount of energy, and if you remember, energy is measured in joules, that can be delivered per SI unit of charge. And the SI unit for charge is called the coulomb, which is given the symbol capital C. So 1 volt is equal to 1 joule per coulomb. So what that means is a current flowing under a potential of 1 volt can deliver 1 joule of energy per coulomb. So as we just said, the coulomb symbol, capital C, is the SI unit for electrical charge. 1 coulomb, technically this is the formal definition, is the amount of charge that's transferred when a current of 1 amp flows for specifically 1 second. Now don't get too lost in all the lingo there. Just really understand that a coulomb is our unit that is representing electric charge. And lastly, the cell potential, which when we're talking about a galvanic cell, is denoted as E cell. That is going to be the maximum potential that a given cell can generate, or a given battery can generate. How many volts or how much potential can our galvanic cell produce? So we denote that with E cell. The voltage or the potential of a given cell will vary with the amount of current flowing through that circuit. And it will depend upon quite a few things. It'll depend upon the composition of what those electrodes are, the concentration of the ions that are in the 2 half cells, and the temperature that it's ran at. So that cell potential, or that maximum potential that it can generate, can vary substantially. You may have seen an instrument before called a voltmeter, and this is what we use to measure cell potential. So a voltmeter has 2 ends, a red and a black end, and they are positive and negative terminals, and you can hook them up to the electrodes of our galvanic cell, and you'll get a reading. We'll get a number that is listed on the voltmeter in volts, and that will tell us what that cell potential is. So the voltmeter always gives a positive reading, and we'll kind of come back to why it's positive in a little bit. And we want to connect the positive and negative terminals to the cathode and the anode, our electrodes. So the positive on the voltmeter gets connected to the positive end of the cathode, and the negative on the voltmeter gets connected to the negative end, or in other words, the anode. And when we have it set up correctly like that, that's when we get that positive reading in volts. The potential that is generated by a galvanic cell is also sometimes called electromotive force, or EMF for short. It's suggested that it can be thought of as a force with which an electric current is pushed through a wire. So the greater voltage, the greater that driving force is. A way that you can kind of think about this is electric current and EMF, we can compare them to the flow of water through a hose. So think about if you have a hose and you have water going through it. The flow of water is like the current, and the pressure of that water coming out of the hose is like the electromotive force, or the EMF. So cell potential or voltage is always a positive value if we have a spontaneous reaction, or one that is occurring without any external influence. So recall what we learned about spontaneous reactions previously. They happen on their own. So if we set up two half cells and we connect them with our salt bridge and we have our wire connecting them and the reaction just takes place on its own, that would be a spontaneous reaction that produces a positive voltage. Because we could have galvanic cells with different half cells that have various concentrations, or they could be at various temperatures, in order to kind of keep things standardized, we talk about something called the standard cell potential. And so that way we can compare the potentials for different cells if we know that everything is standardized. So standard cell potential, which is now denoted as E cell, with that little superscript naught that you see there, is saying, hey, we are at a standard state here. So the reactants and the products are all at their standard state. And specifically, that is, our solutes are at a 1 molar concentration. If we had any gases involved, their partial pressures would be specifically 1 atmosphere. And our temperature is 25 degrees Celsius. So if you remember our original zinc-copper reaction we were talking about right when we started this chapter, we never really talked about what the actual cell potential or the voltage that could be generated from that redox reaction is. And so when we are writing out our electrochemical reactions, we can now include our standard cell potential off to the right after the reaction is written. So remember, we had solid zinc plus aqueous copper ions forming aqueous zinc ions and plating out solid copper. So our zinc was oxidized, our copper was reduced, and notice at the end here now we have this E naught, where the naught is that superscript 0 you see, and this reaction at maximum can generate 1.10 volts is what that is telling us. That is our standard cell potential for this reaction. That is the value there that the voltmeter would read back to us if we hooked it up to the electrodes. And notice that it's a positive 1.10 volts. So that tells us this is a spontaneous reaction as written. This reaction will occur all on its own. So our next goal is to kind of talk about where that number comes from, that voltage that we're seeing, and how we can predict what the voltage will be if we were to hook up any random two electrodes together and set up a battery made up of anything, and how we can kind of relate this back to spontaneous and non-spontaneous reactions. So in order to talk about calculating the standard cell potential, we first need to discuss something called standard reduction potentials. Key on the word reduction here. So each half cell in a galvanic cell will have some tendency to pull electrons towards itself or acquire those electrons. In other words, if it's going to pull those electrons towards it, it's going to proceed as a reduction. And the reduction potential is essentially the magnitude for that half reaction to proceed as a reduction. It's kind of useful, maybe you think about it like a tug of war on the anode side and the cathode side for each of the half cells to pull the electrons toward themselves. One side is going to win because it's going to have a greater reduction potential, and that's the side that's going to end up proceeding as a reduction, forcing the other side to end up proceeding as an oxidation. So once we know those standard reduction potentials for our reduction half reaction and for our oxidation half reaction, we can use them to calculate the standard cell potential, or E cell. So we can calculate that E cell by taking the standard reduction potential for the species that ends up getting reduced minus the standard reduction potential for the species that ends up getting oxidized. The difference between those two will give us our E cell. And based upon what we calculate for our E cell, this value could be positive or it could be negative. If it's positive, we have a spontaneous reaction. If it's negative, we have a non-spontaneous reaction. So still talking about standard reduction potentials, going back to our zinc copper reaction, still using that same one because we have been talking about it a lot. Our oxidation half reaction would represent the oxidation of zinc, where we have solid zinc forming zinc 2+, and that represented the loss of 2 electrons. Our reduction half reaction was copper 2+, gaining 2 electrons to form solid copper. And if we wanted to calculate the standard cell potential, or E cell, for this reaction, we could look up a value for the standard reduction potential for our reduction half reaction, or the copper in other words, and we could look up a value for the standard reduction potential for the oxidation half reaction, which was our zinc one. And if we know those two numbers, which we'll kind of look at where they come from in a second, we can get at our E cell. So once we looked up our standard reduction potential for copper and subtracted up our standard reduction potential for zinc, we would end up with that 1.10 volts, which is our cell potential for this reaction. That positive value would tell me that this is spontaneous because I have a positive number for my voltage. So the voltages that we get for our standard cell potential are dependent upon what those standard reduction potentials are for each of the individual half reactions, for the redox half reaction and for the oxidation half reaction. So next we're going to take a little bit of time and kind of go through a little bit of the background on where the actual numbers that we would look up for our reduction potentials for copper and zinc would actually come from. All right, so try not to get too lost in this little bit of theory kind of background of where the standard reduction potential numbers that we would look up actually come from, but there's really no way to measure the standard reduction potential of just one half cell. You always have to have an oxidation and a reduction reaction hooked up together. So we can only measure the difference between two half cells that are connected. So basically a reference electrode that is chosen and that was assigned, and it was defined as being 0 volts exactly. And that reference electrode that every other electrode is measured against is called the standard hydrogen electrode, or S.H.E for short. So this is what was picked. Everything else is measured against hydrogen, and when we measure that voltage of any other metal against hydrogen, then we can see if it's going to be oxidized compared to hydrogen or if it's going to be reduced compared to hydrogen, and we can read the voltage from the voltmeter, and then that number is essentially assigned as the standard reduction potential for anything else, since hydrogen is defined as being 0 volts. So let's take a look at the standard hydrogen electrode. And what it is it's an inert platinum electrode that is in contact with hydrogen gas, specifically at 1 atmosphere pressure, and then it's also in contact with aqueous hydrogen ions in solution, specifically at 1 molar, because it's standard state conditions. So 1 atm of pressure, 1 molar solutions. And whether hydrogen ions are being reduced to hydrogen gas or whether hydrogen gas is being oxidized to hydrogen ions, the potential is defined as being 0 either way. So it doesn't matter if it's an oxidation occurring at the hydrogen electrode or a reduction occurring at the hydrogen electrode. That is assigned as being 0 volts, no matter what. So then what we can do is hook up any other half cell to our standard hydrogen electrode and see what our voltage is and assign it to the other thing. Since we are saying the S.H.E is always going to be 0 volts, we're assigning it that. So now let's imagine that we hook up our standard hydrogen electrode with a copper electrode in aqueous copper 2+ ions. And let's say our goal is to calculate the E cell, the standard cell potential. We already know what our standard reduction potential of our standard hydrogen electrode is going to be. That's going to end up being 0 volts. But how would this work? So at our anode, where oxidation occurs, this is what is taking place. Our hydrogen gas is being oxidized into aqueous hydrogen ions through the loss of electrons. At our cathode, which is where reduction is taking place, aqueous copper 2+ ions in solution are going to be reduced down to solid elemental copper. And we would actually see this taking place if we hooked this up in the lab. We would visually see that copper is plating out and the mass is getting greater at the cathode, and we would see that bubbling taking place at the anode. So our overall reaction between these two is we would have H2 gas plus aqueous copper ions forming aqueous hydrogen ions and solid copper. That's our overall cell reaction. So the formula to calculate the standard cell potential then, we said, was we take the standard reduction potential of our half cell that's being reduced, which in this case is the copper, and we subtract off the standard reduction potential of our half cell that's being oxidized, which would be the hydrogen, the standard hydrogen electrode. And when we measure this setup of these two half cells connected with a voltmeter, what we end up reading is 0.34 volts. The voltages that you see are going to be fairly small. So 0.34 volts. That is going to end up being our E cell. That's going to end up being our standard cell potential. So we could technically plug that in, 0.34 volts, to our E cell. Now, knowing that our hydrogen is assigned 0, and we know our E cell from our voltmeter, we can calculate any other standard reduction potential for anything else we want to. In this case, the copper 2+, or the copper reduction. So what would this look like mathematically? We have our standard cell potential, E cell, is equal to the reduction potential of our half reaction, that's our reduction half reaction, minus the reduction potential of our half reaction, that's our oxidation half reaction. So in this scenario we have set up, we have our E cell is going to equal our reduction potential of our copper minus the reduction potential of our standard hydrogen electrode. We read from our voltmeter 0.34 volts for the standard cell potential. We know that our standard hydrogen electrode is 0 volts, it's assigned that. So we can get at the standard reduction potential for our copper. And so if we solve for that, it just ends up being the same as the E cell. So our standard reduction potential for copper is going to be a positive 0.34 volts. So if we wanted to write out this electrochemical reaction, that would mean if we had copper 2+ being reduced, so gaining 2 electrons to become elemental copper, we could include after that 0.34 volts. That positive 0.34 volts is the standard reduction potential of copper relative to that standard hydrogen electrode. And I have that positive sign written in there to kind of signify that that's important, because in a minute we'll see that you can also have reduction potentials that are negative as well. What that positive sign really tells us is that that substance, in this case the copper, is more easily reduced than the hydrogen would have been. So the copper ended up proceeding as a reduction, and the hydrogen electrode ended up proceeding as an oxidation. So that's what that positive value for our standard reduction potential for the copper is referring to. Now let's look at an example where we hook up the standard hydrogen electrode with a zinc electrode, and we have zinc 2+ in solution at 1 molar, and compare it to what we just saw with the copper example. So we still have a voltmeter on the top. We're still trying to get at the standard cell potential when we have these two hooked up. So this time, the anode is where the zinc is at, and the cathode is where the hydrogen electrode is at. So at the anode, that is where oxidation occurs. So our reaction for the oxidation of zinc would be zinc solid losing 2 electrons to become zinc 2+. That's our oxidation half reaction. And that means that our hydrogen electrode is going to have to be the reduction one. And we would actually see this taking place if we did this experimentally. So our half reaction for our reduction of hydrogen is going to be 2H plus 2 electrons forming H2 gas. So we took our hydrogen that had a +1 charge down to a gas which has a 0 charge. So it was reduced. And that's at the cathode. Oxidation is still at the anode. Everything we learned about the signs is still true. So if we hook that up to a voltmeter and we read off what we see, we're going to have 0.76 volts for this reaction here. So that's our voltage, that's our cell potential. That's what we would plug in to our E cell. And once again, we know what our standard reduction potential is for our hydrogen electrode because that's assigned. That's a 0 volt. We're going to plug in there. And we can find what our standard reduction potential is going to be for our zinc electrode. Or this is our unknown at this point, what we want to know. So what would our calculation look like this time? Our standard cell potential, which we measured from the voltmeter, is calculated by taking the standard reduction potential for our reduction half reaction, which in this case was the hydrogen this time. This time hydrogen was reduced, minus the standard reduction potential of our oxidation half reaction, which we had our zinc being oxidized. So we've kind of flipped it. Last time our copper was reduced and our hydrogen was oxidized. In this reaction, we saw experimentally that our hydrogen got reduced and our zinc was oxidized. So for our E cell, we plug in our 0.67 volts that we read off the voltmeter. For our S.H.E, we plug in 0 volts because that's what it's assigned. And we can solve for that missing standard reduction potential for our zinc half reaction. And so just mathematically rearranging this equation, we end up getting that our standard reduction potential for the zinc is negative 0.67 volts. So if we wanted to go ahead and write our reaction for our reduction of zinc, we would have zinc 2+ gaining 2 electrons to become solid zinc. And when that reduction occurs, we can include after that equation negative 0.76 volts. And so what that negative sign out in front is just really telling us is that that substance, zinc in this case, is not as easily reduced as hydrogen. So that means that that negative value, well, if zinc is not as easily reduced as hydrogen, it's going to end up being oxidized when it's paired up with the hydrogen electrode, which is what we saw. The hydrogen electrode got reduced, the zinc one got oxidized. So you'll see a mixture for standard reduction potentials of positive values and negative values. And really all that sign tells you is if that substance is going to be oxidized or reduced with respect to the standard hydrogen electrode. If it's a negative value, that substance gets oxidized. If it's a positive value, that substance will get reduced when compared with the S.H.E. Now, you don't have to go through the trouble of those calculations that we did every single time when you want to know what the standard reduction potential of something is. You can simply look it up in a table. But what we were doing was explaining where those numbers that you're seeing on this table actually come from. So if you look on the left-hand side here, you can see that we have a lot of positive values. If you look on the right-hand side here, you can see that we have a lot of negative values. And here is where that half reaction for our standard hydrogen electrode is. And notice the voltage is listed as 0 because, hey, someone wanted to use that as the standard and it's assigned as that. So then everything else is kind of measured with respect to, is it more easily reduced than hydrogen, or is it less easily reduced than hydrogen? And that's where those positive and negative signs come in for our voltages. So now let's find copper and zinc, which is what we just spent a lot of work on understanding where those numbers would have came from on this chart. And this chart is just copied from a book. It's not the one that I have on Blackboard for you guys. The one I wrote on Blackboard is a little bit easier to see because it's in a long list. But if we look on the lower left here, there is our reduction half reaction for copper. And you can see that the cell potential in volts is 0.34, which is what we calculated. And it's positive, so that means that with respect to our standard hydrogen electrode, the copper is going to more likely be reduced. It'll be reduced compared to that. And if we find our other one that we did zinc as another example. Notice it's still written as a reduction. Everything on this chart is written in terms of a reduction, but it doesn't mean it will necessarily occur as a reduction. It's just how this chart was defined as being written as reduction potentials. So our zinc is written as a reduction, but notice we have a negative 0.76 volts. So that tells us that, hey, when zinc is hooked up with the standard hydrogen electrode, it's going to proceed as an oxidation actually, because it has a negative voltage. So hydrogen is going to be reduced compared to the zinc. So this table is really useful because we can just quickly look up these reduction potentials when we need them in order to calculate the overall standard cell potential for any battery that we want to make. Lastly, I want to show you the standard reduction potential chart that you will be able to use on a quiz or exam, and you'll probably want to use on your homework. So I wrote this one because it's a little bit easier to see and compare everything with the standard hydrogen electrode. So what you're looking at here is everything is written as a reduction. All these half reactions are written as reductions, and a positive value means that the forward reaction, the reduction reaction, is favorable. Whereas a negative value means that the reverse reaction, if you were to flip that reaction around and write it as an oxidation, is favorable. So starting kind of with the S.H.E as a midline, as we go up from here on this side, this is representing our increasing ease of oxidation. So all the way at the top, that would mean that something like F2, that's going to be our strongest oxidizing agent. And if we look on the flip side now, below the S.H.E, as we go down the list, this is representing our increasing ease of reduction. And so on the opposite side of the arrow, like lithium, for example, all the way down here, solid lithium, that would be our strongest reducing agent. So remember, a reducing agent is something that gets oxidized itself. So lithium really doesn't want to exist as solid lithium. It would much rather be oxidized to lithium plus 1. And an oxidizing agent is something that is going to get reduced. So fluorine, F2, would much rather exist as fluoride anion, F-, being reduced to that by gaining electrons. And so we can use these values for the standard reduction potentials in order to calculate the cell potential for any battery that you want to make using pretty much any of these substances. And depending upon what you use, you'll get a cell potential that could generate more volts or less volts.